Hello, everybody. I'm Dr. Shafiq, and I would like to welcome all of you in this video session. Today, we'll be talking about shear strength of soil, and we will also talk about how we can find out the shear strength using direct shear tests. Okay, so you can see here, this is a figure where the soil of the slope has failed because of the shear failure, and you can see the soil mass has moved on the street here, the highway here. Okay, so that's kind of like shear failure of soil can do. Okay, now let's move forward. Uh, you can see here that the strength of a material is its ability to withstand and apply the stress without failure. Okay, so a strength is considered in terms of compressive strength when you try to push together, and then tensile strength when you try to pull, and the shear strength that happens like in the interface of the uh, two material. Okay, so you can see that one here. These are the three different type of strength. Uh, Now, strength of a solid material is a little bit different than the strength of soil. So we need to see that actually what is the strength of a solid material. On an atomic level, the molecules or atoms always try to find an equilibrium position and distance among others due to different atomic molecular forces. So strong molecular force. So if there is any external force on the material try to destroy that equilibrium, then the intermolecular forces try to prevent that one. Now, solid materials always try to oppose any kind of activities, and that's basically the strength, that how much force they can oppose. So these phenomena prevailing on an atomic level are therefore similar for all types of stress. Like you can see here, this is like a steel cylinder. So if you try to see that what would be the tensile strength, compressive strength, and shear strength, they are kind of very similar. Okay. Now for soil. Soil is basically a conglomeration of discrete microscopic solid particles. You can see here, this is a microscopic picture of the soil. You can see this is a quartz, means like your sand particle. Here is quartz, here is quartz. This is a clay particle. And definitely you have some organic matter like rotten leaves or other type of stuff. And then you can also see there are a lot of bacteria in soil. And you can see there are some voids here. So these voids are filled with air, and these voids are filled with water. So that's basically the soil. So the particle in soil might have little or no cohesion to each other. If they have like cohesion means like stickiness. Okay, so two quartz particle means like sand particle. When they are completely dry, they don't have any cohesion between them. Okay. On the other hand, clay minerals or clay particles, they usually have some cohesion. Now, when any force is applied to soil, then failure occurs at the interface of the particles instead of the particle itself, which is very, very different than solid material. You see, if I apply any force here, then actually this quartz is not gonna break down, or this one is not gonna break down, or this clay particle is not gonna break down. What will happen that the interface here in that line you can see here, they will just slide each other, okay? So that's basically the failure mechanism for soil. So the strength of soil depends primarily on the interaction of the soil particles instead of the molecular interaction of the particle itself. Okay, so how tightly they are held to each other. That's basically the soil strength. Now, the strength of soil, we can just say that one, that the strength of soil is its ability to withstand and apply the stress without failure or significant deformation, okay? The tensile strength of soil is very, very low. So we usually don't, like apply any tension onto soil. And because of the nature of the soil structure, discrete particles, so shear strength, like is the governing property of soil. So soil fails much earlier because of the shear than it fails um, on compression. So basically shear strength is the governing factor for failure for soil. That's why many times when we talk about strength of soil, we automatically say that this is the shear strength of soil, okay? Now, shear failure of soil. Shear strength of soil is its intrinsic capacity to resist, like forces that cause internal structure of material to slide against itself. So when the shear stress is higher than the shear strength at any particular plane, then shear failure occurs. So you don't have to just apply force like this, but you can understand that when you apply vertical load, the stress can transform in every plane, and in any particular plane, if the stress is higher than the strength of the soil, then basically the failure will occur. So you can see this is kind of a slow failure, and this is your shear failure plane. This one is failing along that line. Again, you can see this building has like toppled, like here, and some soil has moved from here to here. So that's a kind of shear failure you can see. So shear strength of soil depends on some of this stuff that we need to talk about. The primary depends on the strength of soil comes primarily from interaction of the faces of the particle. So this one is interparticle friction between two particles and interparticle locking. And then I'm going to show that one in the next page, okay? And then cohesion among particles. That comes from the surface tension and static charge on the soil surface, okay? Now let's take a look here that what is friction between soil particles, okay? So if you just try to shear that soil here, then you can see they have to move, like they have a surface of contact here and they have friction there, right? So the frictional resistance is basically a function of normal force or confining force, that how tightly this one is held down there. Let's think about like this picture here. So let's say this is a book on a surface. And if you want to push that one, you can easily push that one in this direction. But when you apply a huge normal force on top of that book, then you will see it's very difficult to now move that book from there, right? You can just do a normal check with your book on your desk, okay? So as the confining stress is increasing, your shear resistance is also increasing. So if you don't have any confining stress, then basically you cannot even like make any shape with dry sand, right? It doesn't stick together. So somehow you have to apply some confining pressure so that the soil can get its shear strength, okay? Now, the second thing is coefficient of friction, that how these particles are, do they have very plain surface or they have like angular surface, or how they are connected to each other? Like, is it like connected like this or is connected like this? So this one is easy to move, but if you have like something like that, interparticle bonding is very tight, then basically you cannot move that one, okay? Now, coefficient friction could be changed due to presence of water in between two surfaces. So that's why we see that after the rain, actually the soil strength goes minimum. Okay. Now interparticle locking. So interparticle locking depends on confining pressure again, angularity of the particle and distribution of the size of particle. So we talked about confining pressure. Now important is angularity of the particle. Okay, but how like if they are like all like a sphere like that, then basically it's very easy to move around here. But if you think about here, this is very good interlocking. So you can see it's very difficult to move because that they are interlocked. Each of the particle is interlocked with the other particles. So if you want to shear along that line, so you have to move this particle above here or this particle above here, or have to break that one there. And that's very difficult to do. Okay, so definitely this soil has higher strength than this one. So interparticle locking is very, very important. And that depends on basically soil particle shape as well as the compaction. Now, for any given soil, frictional force due to interparticle locking depends on the confining pressure. So you can see confining pressure is very, very important. It's coming again and again. Okay, that how much confining pressure, or like the pressure this one is trying to hold the soil together. Okay. Cohesion due to surface tension. So you can see soil can hold significant amount of moisture after drainage due to gravity. The water molecules at the surface do not have other like molecules on all sides of them, and consequently they cohere more strongly to the solid surface. So you can see if this is like a very thin tube, if you just put that one, you will see some of the water will go here. That's basically because of the surface tension, right? So when we are talking about soil particles here and they have voids here, so some of the water will drain out, but some of the soil will remain at the corner, tiny corner of the soil particles, and that will try to hold together because of the surface tension. So cohesion in clay soil is more pronounced than the sandy soil because they have smaller pores. Smaller pores means like higher surface tension. Okay. Now there is another reason for cohesion, which is called because of the negative surface charge. So clay particles has negative surface charge, right? That's what you learned earlier. Now, why they have that negative surface charge? Because of the isomorphous substitution, absence of cations in crystal lattice, and absorption of cation and presence of organic matters. So that's basically the reason that why they have negatively charged, but actually all clay particles have negatively charged. Some of them higher negatively charged, like montmorillonite clay has the highest surface charge than kaolinite or illite. Now, since they have higher, negative surface charge, so they try to attract more water when there is no other, like element present there, and they will try to, like the soil particle will try to shear the water particle together, and that's why they create some cohesion between particles. Okay, so this type of cohesion is only available for clay soil because your sand doesn't have any negative surface charge and it doesn't very little, and that's why they don't show that much cohesion when they come to contact with the water. Okay. Now let's try to summarize that what is basically the shear strength of soil depends on. So first of all, interparticle confining pressure. That's basically the effective stress. Okay, effective stress is basically what? The stress taken by the soil solids, not by water. Okay, So effective stress, that depends on the draining condition, such as drained or undrained condition. Because if it is undrained condition, then basically if we apply load to soil at the beginning or undrained situation, all the load will be taken by your um, water, not by the soil particle. So actually you are not changing the confining stress. So basically you can see your effective stress is basically your total stress minus your excess pore water pressure. So these two things are very important. First of all, like the confining pressure, and confining pressure depends on the drained and undrained condition. And the second thing is your cohesion. That's actually the soil property. That coefficient of friction among soil particles called phi or phi prime, that depends on size and shape of particles, packing of the particles, which is normally an over consolidated soil. And the second part is cohesiveness of soil particles. Actually, that's the C primes, depends on the surface area and the charge. So soil properties, basically this one and this one, we call that one shear strength properties of soil, phi prime and C prime. So anybody asks you that question like, hey, what is the shear strength parameter of the soil? This means like they are asking about the phi prime and the C prime. Okay, what is the frictional angle and what is the cohesion? These two are called, I'm repeating because this is very, very important, that shear strength property of soil is basically the phi prime and the C prime. Okay, and your shear strength depends on soil property as well as the confining stress. Now let's move forward. That's a simple block example, like what I was talking in the, like the other slide. So this one, if you take a look here, that let's say this is one soil particle and there is another soil particle and this is the contact surface here. And you try to move that one or try to share that one in this direction, okay? So if you see this figure, then you can see this is P and this is the weight of that particle here. So the normal force would be a normal force equal to P plus W, okay? Now, if you see that maximum, like resistance this one can offer is basically mu multiplied by N. N is the normal force, mu is the coefficient of friction, okay? Now you can see that just before failure, actually that S has to be equal to your F. So if I show that one, S is equal to SF means like the failure at the time of failure is equal to F is equal to mu by N, mu multiplied by N. Now, if you divide equation 1 with the surface, contact surface, like here is the contact surface. Let's say the contact surface is A, then SF by A equal to mu into N by A. But by definition, SF by A is equal to your tau F, means like shear stress. And this one is basically your normal stress, right? So you can write that one that this is your tau F because that's basically the shear stress just before failure or at failure is equal to the normal stress multiplied by mu. Now, mu is basically tan phi prime by definition, okay? So you can write that equation from here that tau F is equal to, means like your shear strength is equal to the normal stress multiplied by tan phi prime. Now, if you have cohesion between soil, because we didn't consider that one here, then basically we will get another term here which is sigma prime tan phi plus C. C is the cohesion. Okay. Anyway, we just try to plot that equation here, and if you see, this is your sigma and this is your tau f. So this is your sigma and this is your tau f. So you will see, like, for three different tests with three different sigma, sigma 1, sigma 2, and sigma 3, I change that confining stress and try to find out that shear stress here by changing that force here, and I get three stress strain diagram from there. I just try to get the peak from there for each of the cases. What would be my shear strength for that particular confining stress or particular normal stress? And then we get a plot like this. So this one is the normal stress. This is the shear stress. And then you get this line here. This angle is phi. Okay, so you can see the equation looks like tau f equal to sigma prime tan phi. Okay, so now this is kind of important, like where do you get your shear strength? Because if you look at the um, stress strain diagram, like you just put like certain P here and then trying to increase that one little bit and measuring that how much displacement is occurring. And then if you plot your shear strain versus your shear stress, then basically you can get a curve like that. Now, some people are saying that, hey, I want to take the peak as the strength. Some people are saying that, no, I want to take this one like the ultimate strength here because the peak will go down. So there are a lot of, like debate on that. So we just see that there are 4 different criteria of failure to determine the shear strength, which are as follows here: that peak strength, critical state strength, residual state strength, and limiting strain strength. Okay, now let's see one by one so that we have a very clear idea that when we can say that this is the, like the shear strength of the soil based on the type of failure. So this one is for peak strength. You can see the peak stress criteria is one of the most common one, okay, because it's very easy to predict. So if you draw the shear displacement versus your shear stress, then basically you get a curve like that, okay? But this is only true for dense sand, okay? For loose sand, actually, we don't see any peak there. This one just goes like that, but still we take the highest from that, like from that curve here, okay? So this criteria is less complicated. Peak is significantly pronounced for dense sand or over consolidated clay. For loose sand and normally consolidated clay, actually, it doesn't show the peak that well, okay? So that's the criteria most of the time we use. Now, the second criterion is critical state, like strength. What this one is trying to say that if you see the critical state strength is identified when the soil undergoing shear at a constant volume, also called the critical state. So if you see that usually, like if your soil is dense, then basically your volume goes down a little bit and then volume goes up, okay? I'll try to show that one why the volume will increase because of the shearing in later, slide. On the other hand, you can see for loose sand, the volume goes low here. The volume goes down. Okay, so this is negative and this is positive. Now you can see the critical state shear means like when this volume is not changing anymore. Okay, you can see this is a straight line that's changed from here to here and then here to here, but from here to here it didn't change. Similarly, for loose sand, you can see this one didn't change here anymore. This is kind of straight here. So we just take the strength when that volume of that specimen is not changing anymore. So we just try to take that one from here. So this is the critical state shear strength. Okay, for this one and also for this one. Okay, now we can also see here that the critical strength is independent of the initial density or packing of the soil grains. So if you remold the soil, like bring it from the field and then remold the soil, then basically your strength, like if you consider the critical state strength, then basically it doesn't depend the initial packing thing. Okay. At the point of shearing, no inherited bonding of the soil grains affect the soil strength. So basically remolded soil will provide you the very similar shear strength than the soil collected directly from the field. Okay. Now the void ratio of loose and dense soil is same at critical state, called the critical void ratio. So you can see for dense sand, the volume is actually increasing. Okay, and here the volume is decreasing. Then you can see at a certain point, they are not decreasing anymore, because this dense sand, if you try to shear again, then this one will go like this. And for loose sand, this one is going to go like this and go straight from here. So from here to here, you can see the void ratio is not changing anymore. Okay, that's basically critical state or critical void ratio. Okay, now let's the third one go, the residual stress, which can occur basically for clay soil, because clay soil are kind of like plates. Clay particles or clay sheets are like plates. Okay, so what happens, like once you apply load to the soil, they are like dispersed soil particle will just align there, and they will form a slick inside. Okay, that they are now kind of like at the beginning they have been like this, and now they have like this, like just moving very slowly. So you can see even the soil has, you can see that the soil has failed here, but actually no, you can see they have some residual strength even after failure. They have some strength there. In sand, we don't see that kind of uh, phenomenon, but here we can see this kind of phenomenon for uh, clay soil, and this one is called your residual shear strength. So basically this residual shear strength is much lower than your peak shear strength, and your design could be a little over conservative, like if you use this residual shear stress. Now limiting strain, like this is your stress strain diagram, and if you see the soil is going like for a very high like strain but still not failing. Okay, but many cases actually the failure not only means like just it failed, but also highly deformed, right? So in that situation, we just take a criteria here that like, hey, we'll take the strain at, let's say like 2%, it like a 5% strain. That's the limiting strain. That like the, hey, 3% or 5%, and then I would just try to say that, hey, what is the strength at that time? Okay, that's basically your limiting strain. Now, Mohr Coulomb failure envelope. that where the soil actually failed. Now, Mohr Coulomb, they proposed a relationship, what I have been showing you in the previous um, uh, slides, that your tau F means your shear strength is basically sigma prime tan phi prime plus C prime. Okay, so this is your shear strength. This is your confining stress, effective confining stress. This is the angle of internal friction, and this is your cohesion. Okay, but you can see that normal basically depends on your shear strength depends on three things here: this, and this. But you already know that phi prime and C prime is the soil property, and sigma prime, that's basically depend on how much loading and drainage condition. If it drain easily, or all the water can escape very easily, then your whatever is your, like a normal stress, that would be your also your effective stress, because your pore water pressure would be zero. On the other hand, if the soil doesn't drain, and if you apply uh, huge loading, but actually this loading is not going to the soil, it's just remaining in the water. So your normal stress is not changing. So your shear strength will not change. Okay. So you have to be very careful that this is not only the um, normal stress, but you have to make sure that the effective normal stress has to be changed if you want to change that one. Okay. The shear strength. So that's your Mohr Coulomb failure envelope. Like if you draw that equation here, let's say this is your x-axis and this is your y-axis, then you can see this one is like this. Okay, so your shear stress y equal to mx plus c. So m equal to tan phi. So sigma tan phi plus c prime, that's basically your y. Now, if you apply soil that and plug that effective stress versus your shear stress, and if you get that one here, this means like this is below the failure line, so the soil is not going to fail. Okay, now if you increase your shear stress, then basically this one is going to move to here, and as soon as touches this failure line, means like this one is going to fail. Okay, again, this is another point C here, which is actually above the failure plane, which means like you cannot go there before failure. Okay, so this is kind of a fictitious now uh, point here, that you cannot go there because the failure will occur before you go to that particular stress. Okay. Now, inclination of the plane of failure. So let's say you took a soil sample here. This is your sigma 3, and this is your sigma 1. And sigma 1 is higher than sigma 3. In that situation, how the specimen will fail. So this one is, we are assuming that this one is making a theta degree with your x-axis. Okay, theta degree. Now you can see if I draw the Mohr circle from this one, so this is my center, which is basically sigma 1 plus sigma 3 divided by 2. That's the distance here. And what would be this one here? That would be your radius, which is basically sigma 1 minus sigma 3 divided by 2. So you have to just draw the Mohr circle here from these two parameters. Now draw the Mohr Coulomb envelope from that equation here. So you can just get that equation here. Okay. Now, if you see that this one is touching at point D with that Mohr circle, so that's basically the failure plane. If you just draw a line from the center to D, that would be your angle twice theta of this one, right? But why this one is twice theta, not theta? Because you know that in Mohr circle, actually the angle would be always doubled, right? Now, how can I find out this twice theta? So if I see that this angle is alpha here, okay, let's say this is alpha here. So twice theta plus alpha, that's basically 180 degree. Again, if you think about this triangle, then basically this is your phi plus 90 plus alpha, that's basically equal to 180 degree. So if you just try to solve that one, then basically you get your theta is equal to 45 plus phi prime by 2. So if you know the friction angle of the soil, then basically you can predict that where this soil is going to fail, at which plane this one is going to fail. Okay. Now let's try to find out the relationship between sigma 1 and sigma 3. Sigma 3 is the confining stress, sigma 1 is the stress that's coming from the top. Okay. Now you can see that from that figure that this is your center, which is sigma 1 plus sigma 3 by 2, 0. And this is your radius here, sigma 1 minus sigma 3 by 2. Now from that figure, you can see AD means like A to D, that's basically the radius of the soil, which is basically sigma 1 minus sigma 3 by 2. OF means like OF from here to here, that's basically C prime cotangent phi prime. And OA is basically the distance from here to here is basically this. Okay. Now, so AF from here to here is basically from OA plus OF. So if we add this one plus this one, that's basically your AF. Now, if you take the sine phi of this one, of that angle, because this is 90 degree here, that's basically equal to this divided by this. Okay, now this one is radius, and AF, we already found that out. That's basically this. Now, if you simplify that one, then basically you will get finally this one here, that your sigma 1 prime is equal to sigma 3 prime tan square 45 plus phi by 2 plus 2 c prime tan 45 plus phi by 2. Actually, we have to remember this equation, and it's also given in your FE reference handbook that you need that one to solve any problem, okay, from this chapter. Now, typical values of frictional angle. You can see the what type of soil you are talking. These are the typical values like loose, medium, and dense, rounded grain sand. So that varies from 27 to 38. If this is angular grains, then basically you can see it can go almost like 45 degree. Gravel with some sand, that's actually can go up to 48. Okay. And for seals, that varies from 26 to 35. These are just, like for your understanding that what might be the range, but actually we have to find that out in the lab for any particular soil. Okay. Now, stress transformation. You already did that one, and I'm just trying to review a little bit because we need to use this equation here. Okay. Now you can see, let's say this is a element, and you have like your sigma x, sigma y, tau xy, tau xy here, and any particular plane here, okay, which is making theta with the x-axis, then basically your normal stress at that particular plane, which is like this one here, normal to that surface here, is sigma y plus sigma x by 2 in plus sigma y minus sigma x divided by 2 cosine twice theta plus tau xy sine twice theta. And what would be the shear strength at that particular like stress at that particular plane? That would be tau n sigma y minus sigma x by 2 sine twice theta minus tau xy cosine twice theta. The angle of principal stress, that tan 2 theta p, is equal to 2 tau xy divided by sigma y minus sigma x. Now, why this one is important for us to find out the shear strength of soil? Now we can just see the example here, that if you know all those things here, then just you can find out the normal stress and shear stress and any particular plane here. Okay, so a soil element is shown below. The magnitude of stress, sigma x 120, tau is 40, tau xy actually, that's 40, sigma y is 300, and your theta is 20 degree. Determine the normal and shear stress on the plane AB. Now, when you are trying to use the formula, then you have to remember two things. First of all, that counterclockwise, like here, right side upward shear is positive. Here I see this one is downward, so this one has to be, tau has to be negative 40. Okay, that's the first thing here. And second thing, whatever angle is given there, your actual angle theta in that equation is always measured from the x-axis counterclockwise. Okay, counterclockwise from the x-axis. If like this one is like this and this angle is given like 20 degree, then basically your theta is not 20 degree. Your theta has to be x measured from the x to the counterclockwise direction. Okay, so once you get that thing, you just plug those in that equation and you can find what would be your sigma n and tau n in AB plane. Okay, we have to do that one again and again because we already know that if I know the phi prime or the friction angle, then basically I know where this one is going to fail. If I know that angle here, which is 45 plus 3 by 2, then I can find out what would be my shear and normal stress in this particular plane AB. Okay. Now simplified stress transformation. What is simplified? You can see there is no shear force here. No shear force here. That's basically the load coming from any building or bridges. You can see only the load is coming vertical. You don't apply any load in this direction, right? So that will make your life a little bit, like easier. So if you don't have any shear here, means your shear is 0. This means like your CD is basically the principal axis, right? And CB is also the principal axis. It doesn't have any shear on that particular plane. But that doesn't mean that the plane AE doesn't have any shear. You will see that actually the soil will transform and make some shear along that line AE. Okay. So anyway, so in that particular situation, when we simplify that one, which is basically the case for most of the soil, like case here. So you can see that tau part here is gone now. We don't have the tau part here anymore because tau xy equal to 0. Okay, so if you just go back here, So this one is 0 because tau xy equal to 0. This one is also 0, and this one is also 0. So you get this one. So your principal stress angle is 0. So this means like this is your principal stress, principal plane. Okay. Now, how do we draw the Mohr circle? You already know that one, but we are just trying to refresh our memory a little bit. So you can see here, this is an element here. You can see this is sigma x, this is sigma y, this is tau xy, this is tau xy here. So how do you draw the Mohr circle from there? So the first thing we have to find out the radius, location of the radius. The location of the radius is like xy plus x sigma x plus sigma y by 2, 0. That's the location. Now we have to find out, hey, what is that radius here? That's basically sigma x plus sigma y by 2 plus tau xy and then root over this. Once you get that one, then from that center you draw a circle. That's your Mohr circle. Okay. Now, how did I get this twice theta angle from there? So first of all, I have to find out that point R and M. These are nothing but the position, like the stress on this plane and this plane. Okay, so this plane is, you can see, right side upward. Okay, or we can just say like when this one rotates counterclockwise, then basically this one is positive. Your tau xy is positive when this one tries to rotate counterclockwise along the element here. So you can see here, this is positive tau xy and this is negative tau xy. So that's the difference here. Sigma x, and this is positive tau xy. Here is sigma y minus negative xy because it's trying to rotate clockwise. That's why it's negative. So that's basically the DC is kind of the plane here. And this one actually, like DC or AB, this angle, this plane makes an angle theta with that. So if you measure twice theta from there, actually you will find that point Q, and you can, this is basically, you can read the normal stress and shear stress from the graph, and then you can just find out this one. So Mohr circle is basically the graphical method, right? You can use the values directly from the formula. Now, if you want to do that one using like the graphical method, then you can draw the Mohr circle and read the, like values from there. Many times we also draw the Mohr cycle to be more clear that actually what we are going to do here. Okay. Anyway, we talked about that here. Now let's see here. This is the simplified case. You can see you don't have any tau xy. So this is sigma 1 and this is sigma 3. So this one is sigma 1 plus sigma 3 divided by 2, and your radius is just sigma 1 minus sigma 2 divided by 2. So you can just draw that one here. So this is your sigma 3 minor principal stress, and this is your sigma 1 major principal stress, and then basically this is your plane DC. So DC is basically your principal plane. So from principal plane, if you go like twice theta, then basically you can get that point Q. Now read that sigma n and tau n from there. So you can get the sigma n and tau n from that particular point. right? Again, this is like a graphical method. If you want to find out your sigma n and tau n from the formula that I showed you earlier, you would definitely get the same answer, okay? Now, this is a very important thing that we use all the time in our um, for soil mechanics, which is called the pole method to determine the stress. We just try to find out the pole, which is called the P. This is a unique point on a Mohr circle, okay? Let's say here, I just try to find out how I can find out the pole, okay? So I can either consider this plane or this plane, doesn't matter. Let's say I'm considering this one here. So this one here is 150 and this one is positive 60, right? So 150 and positive 60, that's basically this point here. Now what I have to do, since I chose DC, so once I get that point, so I just draw a line which is parallel to DC from that point in. And that's the point, like called P. This line intersects with this circle at P, so this is your pole. Now you can say like, hey, I want to do that one from here. Okay, this is 90 and this is negative 60 because this is trying to rotate clockwise. So 90 and 60. So this is the point. Now I have to draw a line which is parallel to BC. So if I do that one, then basically you see I come to that point at P. So P is a unique point. Doesn't matter whether I use this or this or this or this. All the time I get this point P there. Now, how can I find out the stress in a particular plane AC? If I want to find out the stress at AC, then basically I have to draw a line from P, which is parallel to this line AC. So PQ is parallel to AC here. Okay, so this one touches this point here. So you can read it from the graph that, hey, actually this point is 60, 30. Okay. Now let's say I'm talking about another plane here, DE. So how do I know the shear stress and normal stress at that plane DE? So I have to draw a line from P from my pole, which is parallel to that line DE. And this one intersects at that point. So basically I have to read that one from there and I can find out the shear stress and normal stress at that particular point. But again, your Mohr circle is basically a graphical method. You can just do all those things using the formula and direct without drawing that Mohr circle, you can just calculate, like most of the stuff there. Okay. Now lab test for shear strength, how we can find out the soil strength in the lab. Then the most commonly used laboratory methods to determine the shear strain parameters of soil, which is C, C prime, Phi or Phi prime. C means like actually cohesion, total cohesion. C prime is the effective cohesion. Phi is the kind of like if angle of internal friction in terms of total stress, and phi prime is basically the angle of friction in terms of effective stress. Now we can do either direct shear test or we can do triaxial test. So there are 3 different triaxial tests here. So depend on like the situation at the field, we have to pick that which one we are gonna do. I'll talk about one by one later on in my other lecture, actually for triaxial test. But here I'm gonna talk about direct shear test, which is very, very common especially for clay, for sandy type of soil. Okay. There are some other tests to find out the shear strength, which is called the direct simple shear test, plane strain triaxial test, torsional ring shear test, but those are only used for academic and research purpose. Okay. So if you see like most of the lab in town, like, hey, what are the tests they can do there? That basically these tests here, direct shear test and triaxial test. Okay. Now let's talk about direct shear test. That's the direct shear test instruments. Okay, you can see here, this is the shear box here. I showed that one separately here. Okay, and this one is trying to move this shear box here. So you can see if you look at the shear box here, you can see there is two parts there. Okay, like one part is top of another part, and they don't have any lock into it. So you can see here that I put these two parts of that box. This is the cross section of the box. Okay, so put this two part of the box together, and then basically there is a screw here. There is a screw here just to make sure that this part doesn't move, like when I feel the soil here. Okay, so I feel that soil here, and then I just put like that, like loading, normal loading thing here. And this is a vertical strain transducer to measure like how this one is going to move when I apply shear. And you also have this horizontal strain transducer that you can measure that how much this one is going to move. Now, what we are trying to do after setting all that thing, we are just going to bring that one here, and then basically we are going to push that one in this direction, the bottom. Okay, and try to see that this one is causing how much horizontal strain and how much vertical strain, as well as how much force I need to move that one. Okay, so before that one, you must have to remember that you have to take that, like the screw off from there so that they can just freely move from here to here on only the soil is trying to, like protect that movement. So you can see here, actually, that's the way soil has moved. Okay. Now let's try to see here that what is the step-by-step procedure for your shear test, direct shear test. So first of all, you have to fill that whole thing here and then apply that normal load here. Okay, so we usually run that test for 3 different normal load or 3 different normal stress. We can just find out that load divided by the area of that box. That's basically your normal stress, right? So let's say we try to do that one. Let's say 20 kPa, 40 kPa, and 80 kPa. Okay, so we have to run that test for 3 different times with 3 different normal loading. Okay, so after applying that normal loading, let's the soil consolidated. Actually, since we do that one, like for sandy soil or silty soil, it doesn't take that long to get consolidated. Now, increase the shear force T slowly enough that the soil can drain until it fails. So I'm just going to try to move that one now. Okay, try to move that one now and increasing my force here. I can increase that force 2 different ways. One is just stress controlled. I just increase the stress little by little. And the second thing is like I'm just going to move that one at a certain strain, and that would cause the stress higher. Okay, so the 2 ways you can just go forward. Actually, in our lab we have the strain controlled, means like this one is just trying to move at a certain velocity, like in that direction, and try to see that how this one is going to change. Now you can see if I run 3 tests, like them, and draw the stress strain diagram. So for sigma 1, I get like this, sigma 2, I get like this, and from sigma 3, I like this, and I try to find out the shear strength based on peak strength. So I can find out the peak stress from there, that is a strength here. So for sigma 1, this one is your tau F1. For sigma 2, this is your tau F2, and sigma 3, this is your tau F3. Once you get that 3 different points here and run that one for 3 times, once you get that thing, then actually like they are talking about 3 to 4 different normal loads. 3 is fine, 4 is better, okay? And then draw the curve like from there, like your sigma in the x-axis and your tau in the y-axis. So you get a curve like that, okay? This is your normal stress and this is your shear stress. And then basically you plug that 3 points like sigma 1, tau F1, sigma 2, tau F2, sigma 3, tau F3. And then if you draw the line here, that basically your Mohr Coulomb's line. Usually this one passes through 0 for sand or normally consolidated soil because your cohesion is 0 there. I'm saying that one again, like for sand and for normally consolidated soil, your C is always 0, your cohesion is always 0. Okay, so this one passes through the origin. Okay, so your C equal to 0. If you just measure that angle here, that's basically your phi. Okay, so for that particular soil, since this one is passing through the origin, you can say the shear strength parameter of the soil C is equal to 0 and your phi is equal to whatever you measured from here. Okay, so that's the way you try to find out the shear strength for sand and like sill type of material. Now you can ask like, hey, can you do that one for clay? Well, we'll talk about that. It's a little bit difficult, okay? And why difficult? Because we cannot control the drainage here. Now let's move forward. So for direct shear test, you see for dense sand and over-consolidated clay, they show a very distinct peak here. On the other hand, loose sand and normally consolidated clay, they usually show, they don't show any distinct peak. So you can see this one looks like this, okay? Now the volume of the dense sand and over-consolidated clay increased during that shearing. So that's basically your dense sand. This is expansion. The volume is increasing, the volume is decreasing. So at the beginning, they will just decrease a little bit, but then they will try to increase and then they will remain at the same line. On the other hand, we see for loose sand and normally consolidated sand, clay, this one, the volume actually goes down and then remains same. So when they remain same, then basically we call that one critical state void, right? You can remember that one. Now, it's a very important question that like why the dense or over-consolidated soil will expand during the shearing. Okay. Now, if you see here in this figure here, that you actually measure the vertical strain from there, right? If this one goes a little up, you can measure that one with this transducer, which is very, very sensitive and can measure like 1,000 of an inch. Okay. Now, if you go there, I tried to show that one in this picture here. Let's say this is the two-part, like before shearing, you can see this is the interface of the particles. Okay. And they are tight. Now, when you're trying to shear them, then basically they have to come out and go up here to get out from this way. So at the beginning, the height was h, and this teeth height is t. So when they come top of that teeth, then basically the height becomes now h plus t. A very small increase in the vertical direction, but actually that's increasing. So you can see if they are just like this, and if you try to move like this, so you have to first come out from there, and then you can just start moving, right? So when they are just trying to come up from there, that's actually the volume is increasing. And then when this one is top of that, then basically your volume doesn't change anymore. So we are almost like a point here that the volume is not changing anymore. Okay, so that's basically the reason. Now, what happens like for loose sand? So loose sand, when you try to do that one, then basically the particle here, okay, the particle here has voids here. So when you try to do that one, then basically this one goes down like this. This one goes down like this, okay? So that's why the overall, like volume decreases because of the loose sand and normally consolidated clay. Now, this is an example to show that what you have to calculate from your data. So following are the results from 4 drained direct shear tests on an over-consolidated clay. As soon as they say like over-consolidated clay, this means like they have C, okay? Who doesn't have C? First of all, if it is sand, doesn't have any C. If it is normally consolidated soil, it doesn't have any C. Okay, now we'll just try to find out from there. Okay, so diameter of the specimen is 50 millimeter and height of the specimen 25 millimeter. So for test 1, 1, 2, 3, 4, your normal force is 150, 250, 350, and 550 Newton. Okay, and the shear force at peak, they didn't show you, they didn't give you the stress strain diagram. Rather, they gave you the peak and the residual shear force. Okay, this is a force, so we have to convert that one to stress. Okay, how do you do that one? We just first try to find out the area. So the area is pi by 4d square. So that's actually this many meters square. So this is test number 1, 2, 3, 4. This is the normal force. When you divide this column with this, that's basically your normal stress. This is your peak shear force. If you divide that one with this, then basically you get this shear, peak shear strength. Then this is your residual shear force. And then you divide that one with the area. So you get, this is your residual shear strength. Now I can draw a curve like the normal stress versus the tau F. And again, that's for peak shear. And then I can draw another graph for normal stress versus the shear stress for residual strength. Okay, now let's go there. So these are the 4 points for the peak shear strength. And if I draw a line here, And this one intersect at this point, which is actually 40 kilonewton per meter square. That's your C prime. If you measure that angle, that's 27 degrees. Okay. Now you are drawing another curve here, which is in terms of normal stress versus the residual shear strength. So they have like 4 points. If you draw the line here, this one goes to the origin and you get that angle, which is 14.6. So for your peak shear strength, your tau F equal to sigma 1027 plus 40, 1027 plus 40. On the other hand, for residual strength, your tau residual is equal to sigma 10 14.6 plus C equal to 0 because it's passing through the origin. Okay, so that's basically the answer. Now, what is the advantage of direct shear test? It's very simple, inexpensive, less time consuming, and good for drained strength. So first of all, it's simple. It takes like inexpensive. It's usually for each of the specimen, they usually charge like $250 to $350. Okay, less time consuming. You can do that one maybe like a couple of hours. Okay, and good for drain strength means like when the soil drain easily, then basically this one is the best method. So it's kind of the best method for, let's say, for sand and silty type of soil. Now, what are the disadvantage? The disadvantage include stress state is unknown. You don't know like the sigma 3 confining stress and the uh, vertical stress. So you cannot draw the Mohr circle from there. That's very difficult to do. Second thing, cannot prevent drainage. So that's why not suitable for undrained strength, especially if you want to find out the undrained shear strength for clay soil, then basically this is not a good method. Cannot measure the shear strain. It cannot measure the shear strain because you should only measure the vertical and horizontal strain, and cannot apply appropriate confining stress. So in the actual field, if you go like 50 feet below the soil has like a confining pressure all the way, okay? But in this method, you cannot change that confining stress in your soil and cannot measure that how much confining pressure coming from the side, right? So those are the disadvantages of these methods, okay? So that's basically like the first part of your shear strength test. In another video, I'm gonna talk about the triaxial test, that how we can do 3 different triaxial tests based on the field situation and um, and and how this one differs from your direct shear test. Okay, so thank you for watching, and if you have any question, please feel free to contact me and come to the Zoom during the office hours. We can definitely discuss about that there. Again, thank you. Bye.